Right now, somewhere in the world, a power plant is pumping thousands of tons of superheated water through its pipes every single minute. If that water stops being cooled, even for a few minutes, the temperature inside the machinery starts climbing fast, and the turbines have to shut down, electricity production collapses, and the entire plant edges toward an emergency failure that could black out an entire region. You would think the fix for a problem this massive would require giant fans and powerful motors humming around the clock. But the engineers who actually solved this problem came up with something far stranger. They built a concrete tower as tall as a 20-story building, and somehow got it to push millions of cubic meters of air every hour without a single motor inside it. The entire secret was hidden in one narrow waist halfway up the structure. Air entering that pinch point would suddenly accelerate on its own, as though an invisible giant fan had just switched on. And here is the part that still surprises engineers. Today, if you took away that curve and built the walls perfectly straight instead, the cooling power would collapse, even though from the outside the tower would look almost identical. There are no blades, no electric motors, no hidden machinery driving that wind. The entire system runs on nothing but heat, gravity, and the shape of the concrete itself. Engineers call it natural draft, but watching it in person feels closer to magic than physics. A building that seems to breathe on its own, exhaling a column of vapor that can be seen from miles away. So how did a simple curve in a concrete wall become one of the most brilliant tricks of 20th century engineering? And why, without it, almost every power plant on Earth would look completely different? To understand how we got here, we have to go back to the early 1900s, when European cities were expanding faster than anyone could plan for. Factories ran around the clock, power stations pushed their equipment to the limit, and entire economies depended on a steady, uninterrupted flow of electricity. In the Dutch town of Heerlen, coal mines and the industries built around them never stopped. Heavy machinery spun day and night, and all that constant friction generated enormous amounts of heat. The obvious fix was water. Engineers ran ordinary water through the machinery to pull the heat away, but that left them with a new problem. Somewhere, that scalding water had to be cooled back down before it could be reused. So builders did what builders always do when they need something fast and cheap. They put up the first cooling towers out of plain timber, the same material used for scaffolding and mine supports all across the region. For a while, it seemed to work, but wood and constant clouds of hot steam are a terrible combination. The moisture crept into every joint, the boards swelled and warped, and rot set in within months rather than years. Crews would patch one section, only to find the boards beside it crumbling apart in their hands. These towers had alarmingly short lifespans, sometimes lasting barely a single winter before they needed major repairs. Factories were forced to halt production again and again just to rebuild structures that should have been standing for decades. And every shutdown meant lost output, lost wages, and mounting pressure from management to find something better. It was obvious that wood wasn't going to cut it long term. And what the industry needed was something durable enough to handle a relentless cycle of scalding water and freezing air without falling apart, and strong enough to do it for generations rather than seasons. That search for a tougher material ran straight into a problem nobody had anticipated: the ground itself. When word got around that something enormous was being planned in the middle of a working-class neighborhood, the rumors started almost immediately, spreading from doorstep to doorstep faster than any official announcement ever could. This was an era of real anxiety, with political tension simmering across the continent and people genuinely uneasy about what their governments might be hiding from them behind factory walls. Some were convinced that these structures were secret testing facilities disguised as ordinary industrial buildings, built deliberately in residential areas to keep them away from prying eyes. Others whispered that the towers were meant to store something far more dangerous than steam, perhaps stockpiles tied to the military buildup everyone could feel coming. People feared, quite sincerely, that whatever was happening inside would poison the soil in nearby fields, wither the grass their children played on, and foul the air their families breathed every day. The real explanation had nothing to do with conspiracy and everything to do with soil mechanics. The ground beneath Heerlen had been honeycombed for decades by abandoned mining tunnels, and that hollowed-out earth shifted and sank unpredictably. Any conventional heavy masonry structure built on top of it risked cracking apart the moment the ground beneath it moved even slightly. Authorities wanted uninterrupted industrial output, but the physical reality of the terrain made that almost impossible with the building techniques available at the time. That is where two engineers, Frederick van Idersen and Gerard Kuipers, came up with an idea that nobody else had seriously tried. Instead of fighting the unstable ground with sheer mass, they abandoned timber altogether and turned to reinforced concrete, but used in a way that defied the conventional wisdom of the era. Rather than thick, heavy walls, they poured a smooth, curved shell barely 15 centimeters thick, shaped like an enormous hourglass. The structure ended up remarkably light for its size, And that lightness turned out to be its greatest strength. Where a rigid, heavy tower would have cracked the instant the ground shifted beneath it, this thin shell could flex slightly and absorb the movement without breaking. But when the first prototypes were tested, the engineers ran straight into a different kind of problem. The structure stood up fine, but the airflow moving through it was far too weak. The scalding water pumped in from the plant simply wasn't cooling down enough before it cycled back into the machinery. Something about the shape of the tower itself was choking off the very airflow it depended on, and the team needed an answer fast. Because every day without one meant another day of underperforming machinery. It turns out a plain straight cylinder is one of the worst possible shapes you could choose for this job. When the earliest designers tried building simple, tube-shaped towers, they hit a wall almost immediately, and that wall was made of cold air. Hot, moist steam from the plant's machinery would rise up through the tower. But the moment it reached the open top, it cooled rapidly and condensed into a heavy, dense cloud. That cloud didn't just float away. It sank back down into the mouth of the tower, sitting there like an invisible plug. The warm air trying to rise from below simply couldn't push through it. Within minutes, the boilers downstream would start overheating again, and nobody had a way to force the air to circulate without resorting to enormous electric fans that would have eaten up huge amounts of the very power the plant was supposed to be generating. The old engineering rule of thumb was simple: build the chimney taller. But a thin concrete shell standing on unstable ground could never support the kind of towering, massive structure that older designs called for. While engineers wrestled with the problem on paper, the rumors around these strange round towers only grew stranger. People in nearby neighborhoods became convinced that structures were artificial weather machines built to control the local climate. Newspapers ran stories claiming the towers worked like colossal vacuum cleaners, supposedly disrupting bird migration routes for miles around. Residents on the outskirts worried that some invisible constant vortex inside the towers could tear apart their homes during a storm. There were even whispers that the military was secretly using the hollow, concrete shells to test acoustic weapons, since the empty interior produced an eerie, booming echo. Locals demanded the experiments stop, never realizing that the unsettling sounds were nothing more than ordinary acoustics bouncing around inside a giant empty shell. The actual solution to the airflow problem turned out to be something almost anyone could understand, because it is the same. Physics behind a trick we have all done in a backyard. Think about pressing your thumb over the end of a garden hose. The moment you narrow the opening, the water shoots out with far more force and speed than before. The engineers realized they could apply that exact same principle to a column of moving air, so they reshaped the tower into a true hyperboloid, pinching it inward at the waist, like the narrow middle of an hourglass. When hot air reached that narrow throat, it accelerated sharply, transforming into a powerful, self-sustaining internal updraft. That rushing column of air punched straight through the layer of cold, heavy air sitting at the top and carried the heat away into the sky. Just like that, the plant had all the cooling power it needed, generated entirely by the shape of the concrete itself, with no motor required anywhere in the system. For a while, it seemed like the problem was finally solved. The engineers had tamed the airflow inside the tower. But nature had one more lesson to teach them, and this time it came from outside the structure in a form nobody had fully accounted for. On November 1st, 1965, in the north of England, something happened that sent a shockwave through the engineering world. At the newly built Ferrybridge power station, 3 massive concrete cooling towers, each roughly as tall as a 30-story building, collapsed one after another within the span of a single hour. A strong autumn storm was moving through the region that day, with rain lashing sideways in gusts, rattling windows for miles around. But the wind gusts never exceeded what engineers had already planned for, not even close. These were brand new structures, finished only months earlier, built from reinforced concrete that everyone involved considered completely reliable. Inside the control room, operators first heard a low, ominous rumble, something that sounded less like weather and more like distant thunder rolling up from underground. When they looked outside, they saw something that seemed impossible. Spiderwebs of deep cracks were racing across the enormous gray walls in real time, branching and multiplying faster than the eye could follow. The structure lost its stability almost instantly and folded in on itself in a cloud of dust and debris. And before anyone could fully process what they were watching, a second tower went, then a third. It was a devastating blow to the country's energy grid, and the massive industrial complex ground to a halt within minutes. Losing 3 of the most critical structures at a major power station in broad daylight with no obvious external cause set off a wave of panic and speculation. Cold War tensions were running high at the time, so newspapers immediately floated theories about foreign sabotage. In working-class neighborhoods nearby, people whispered that the project's management had skimmed money off the budget and used cheap, substandard cement in the concrete mix. A formal investigation was launched right away, while the public, gripped by fear, called for the entire station to be shut down. It seemed almost unbelievable that solid reinforced concrete, 13 centimeters thick, could be torn apart by something as ordinary as wind, no matter how strong, with no other explanation in sight. What the investigators eventually uncovered was far more unsettling than any rumor, because the real cause was a piece of physics nobody had studied closely before that day. The towers themselves had been built to a high standard. The fatal mistake was in how they were arranged on the site. 8 enormous towers had been placed close, together in a single row. When the storm's wind hit the very first tower in that line, its smooth, curved wall acted almost like a nozzle, exactly the same principle that had made the towers so effective at moving air internally. That curve deflected the wind sharply and funneled it at far higher speed straight into the narrow gaps between the neighboring towers. Pressure in those gaps spiked dramatically, creating a powerful suction effect. And by the time the storm reached the towers further down the line, it was hitting them with far more force than the original design had ever accounted for. The thin walls simply couldn't withstand it, and they tore apart. That single afternoon permanently rewrote the rulebook for how cooling towers are spaced, reinforced, and tested around the world, and it's the reason modern towers are built with reinforcing rings and far more careful spacing between neighboring structures. In the years that followed, the entire industry essentially started over from scratch on a question nobody had thought to ask before. What happens to wind when it passes not through one tower, but through a whole cluster of them standing close together? Engineers began running scale models through wind tunnels, deliberately grouping miniature towers in different arrangements to map exactly where pressure built up and where it dropped away. They discovered that the danger wasn't the storm itself, but the way identical curved structures, lined up in formation, could amplify each other's effect on the airflow in ways no single tower ever could on its own. New towers built after Ferrybridge came with horizontal stiffening, rings wrapped around their midsections, reinforced bands of concrete that gave the thin shell extra rigidity, exactly where the wind pressure tended to concentrate. Spacing rules were rewritten, so towers were no longer packed into tight, efficient rows, but staggered and separated by far greater distances. It was a humbling lesson for an entire profession, a reminder that even a structure engineered with total confidence could fail the moment it was placed next to an identical twin. But just as engineers solved the problem of wind hitting the towers from outside, a completely different issue surfaced inside them, and this one threatened to quietly choke a plant's output without anyone immediately understanding why. In the middle of the 20th century, plant operators kept running into a strange, contradictory situation on their control panels. A powerful column of air was rushing up through the tower at high speed, exactly as designed, yet the water collecting at the bottom of the tank was still coming out too warm. Because of that, the steam circulating through the rest of the system couldn't fully condense back into liquid the way it needed to. Pressure built up inside the condensers, and the plant's automated systems were forced to throttle back electricity production just to keep things stable. When engineers finally looked closely at what was happening inside the tower, they found something resembling a tropical downpour. Massive sheets of scalding water were falling from a great height, forming a continuous, heavy curtain. The droplets were simply too large and falling too fast to release their heat into the rushing air around them. By the time they hit the basin below, they were still uncomfortably hot. That constant, thundering waterfall inside an open concrete structure didn't go unnoticed by people living nearby, and once again, rumors filled the gap left by uncertainty. Residents near the industrial zones noticed thick white clouds pouring out of the towers at all hours and quickly developed their own theories about what was really going on. Some insisted the plants were secretly mixing chemicals into the water. Newspapers ran alarming pieces claiming the falling mist was laced with corrosive acid that would ruin crops in nearby fields and eat away at the paint on people's rooftops. Many genuinely believed their government was hiding an environmental disaster from them. None of it was true, but the underlying engineering problem was very real, and it needed a fix. The fix came from a piece of everyday kitchen physics. A whole sugar cube takes a surprisingly long time to dissolve in a cup of hot water. Crush that same cube into fine grains first, and it disappears in seconds. Engineers realized they needed to do the exact same thing to that heavy curtain of falling water. Break it into the smallest possible droplets to expose far more surface area to the rushing air. So they installed a dense horizontal grid inside the tower, thousands of thin plastic and concrete panels known as fill or splash bars. Instead of falling in one continuous sheet, the water now struck panel after panel on its way down, shattering into a fine mist with every impact. The total surface area of water exposed to the air multiplied by an enormous factor. The rushing wind could now strip away the excess heat almost instantly, and the water reaching the basin below was finally cool enough to do its job. Solving that problem, though, created a brand new headache, and this time it showed up far outside the plant's walls. Turning that heavy downpour into a fine mist meant the tower was now releasing enormous volumes of warm, saturated vapor straight into the open air. In the right weather conditions, that vapor would condense almost immediately into thick, low-hanging fog, sometimes dense enough to shut down nearby highways. In colder months, the same vapor could fall as an entirely localized, almost surreal snowfall, dusting roads in the middle of an otherwise mild autumn. This exact phenomenon turned up around several large power stations through the later decades of the 20th century. In western Pennsylvania, meteorologists monitoring the cooling towers of a major coal-fired plant documented the effect repeatedly, year after year, until it became something of a local legend among residents who drove past the plant on their daily commute. The sky for miles around would be completely clear, not a cloud in sight, yet thick white plumes pouring straight out of the towers would settle over nearby roads as a sticky, heavy moisture that beaded on car windshields and handrails. On cold days, that moisture would freeze almost instantly into a layer of fresh snow, covering the pavement in patches that had nothing to do with the actual weather forecast and creating genuinely dangerous, isolated driving conditions right at the plant's doorstep. Locals, understandably confused by snow falling from a cloudless sky, blamed the plant's management for whatever was happening, with no clear explanation in sight, and some even avoided the stretch of road nearest the towers altogether during winter months. That strange, localized weather sparked real debate inside the scientific community at the time. Some meteorologists proposed that the sheer volume of hot vapor pouring out of these towers was effectively creating tiny, artificial heat islands, strong enough to permanently shift local wind patterns and generate near-constant cloud cover for miles in every direction. A few scientific journals went even further, suggesting humanity might have accidentally stumbled onto a tool for genuinely controlling regional weather, one that could theoretically be aimed at drought-stricken farmland to coax artificial rain clouds toward crops that desperately needed it. In reality, that ominous-looking plume was nothing more sinister than pure water vapor, and the physics behind it is identical to what happens above a kettle boiling away on your stove. That white cloud rising off the spout isn't smoke or pollution. It's simply water that has evaporated and is now condensing back into visible droplets the instant it meets cooler air. Inside the cooling tower, a fast-moving column of air was carrying out the microscopic droplets created by the fill system, and once that warm, humid air hit the colder air outside, it condensed instantly into fog or, on a cold enough day, fresh snow. Still, losing thousands of tons of clean, treated water as fog drifting away into the atmosphere was an expensive problem for any plant's bottom line. To stop that loss, engineers added one more piece to the system, a drift eliminator mounted near the very top of the tower. It's built from hundreds of curved plates arranged like an open set of window blinds. As the dense rising vapor pushes upward, it slams into these curves, and the larger water droplets simply drain back down them into the shared collection basin below. Clean, dry air continues rising into the sky, while the valuable water stays locked inside the plant's closed-loop system, ready to be reused. By this point, engineers had mastered nearly every force at play inside and around these towers: the airflow, the wind, the water, the fog. But one threat remained completely outside their control, and on a single afternoon in 2008, it arrived without warning. On May 12th of that year, in China's Sichuan province, the ground tore open in a massive earthquake. In a matter of seconds, the shaking compromised buildings, bridges, and entire industrial complexes across the region. A huge industrial zone nearby was left in ruins, but amid the dust and rubble, rescue crews noticed something that genuinely stunned them. The hollow concrete cooling towers in the area were still standing, almost completely intact. There wasn't a single major crack running through their thin walls, even though the solid brick buildings and heavy industrial workshops standing right next to them had collapsed all the way down to their foundations. On paper, that shouldn't have been possible. These were hollow concrete shells, over 100 meters tall, with walls barely 20 centimeters thick. A team of engineers arrived almost immediately to figure out how these seemingly fragile giants had survived an earthquake that flattened far sturdier-looking buildings around them. They walked the wreckage for days, photographing the towers from every angle, tapping the concrete for hidden fractures, half expecting to find catastrophic internal damage that simply hadn't shown up on the surface yet. What they found instead only deepened the mystery. The shells had flexed clearly. You could see faint hairline marks where the concrete had stretched and recovered, but nothing had given way. For decades before that, the engineering world had been split into two competing camps. The old guard believed in absolute rigidity, the idea that any tall structure facing a powerful earthquake needed to be as heavy, dense, and immovable as possible. Following that logic, designers had spent decades pouring thousands of tons of steel into foundations and building thick, fortress-like walls, essentially turning industrial structures into hardened bunkers built to shrug off any force thrown at them. A newer, competing theory argued the exact opposite. that rigidity was actually the enemy of tall structures during an earthquake, and that buildings should be allowed to flex and sway with the shaking ground rather than fight against it head on. For years, this debate stayed largely theoretical, confined to conference papers and competing mathematical models, because nobody had a real disaster severe enough to test both ideas against each other under genuine, uncontrolled conditions. The Sichuan earthquake settled that argument decisively in favor of flexibility. The tower's secret turned out to be hidden in the geometry of the hyperboloid shape itself and in how its base was built. Instead of resting on one continuous, solid foundation, the entire weight of the structure was carried by a ring of slanted concrete columns arranged in a circle, crossing each other to form a lattice of interlocking diagonal supports. When the ground started shaking violently, that lattice acted like a single, unified, shock-absorbing system. Rather than letting the structure crack under the strain, it redirected the destructive energy of the seismic waves, channeling it upward along the tower's curved walls instead of letting it concentrate at any one weak point. The structure flexed slightly under that force, but never lost its overall shape, behaving more like a resilient shell than a rigid block. In the end, it was the geometry of the tower, not brute material strength, that protected it. Looking back across this entire story, what stands out is how little of it was solved with electronics, expensive motors, or brute force engineering. Every single obstacle, the rotting wood, the unstable ground, the choking layer of cold air, the storm that tore 3 towers apart in an hour, the water that wouldn't cool fast enough, the fog that buried highways in summer snow, and finally an earthquake that flattened everything around it, was ultimately solved by understanding and bending a basic law of physics, rather than fighting against it. That strange, almost alien hourglass shape rising above power plants around the world isn't an architect's flourish or a stylistic choice. It's the end result of a century of trial, failure, and hard-won understanding. A structure built not to resist nature, but to work alongside it. What's remarkable is that almost none of these lessons were learned in a classroom or on a drafting table. Every single improvement came from a failure that played out in public, in front of frightened neighborhoods, skeptical journalists, and panicked control room operators who had no idea, in the moment, whether their plant was about to go dark for good. Rotting timber taught engineers to think in concrete. Sinking mine shafts taught them to think in thin, flexible shells instead of dead weight. A stubborn layer of cold air taught them the value of a pinched waist and a rushing internal wind. A collapsed row of towers in Yorkshire taught the entire world that identical structures, standing too close together, can turn into each other's worst enemy. A curtain of water that refused to cool fast enough taught them to think in droplets instead of sheets. And finally, a province in China shaking apart beneath ordinary buildings taught engineers that sometimes the strongest structure isn't the one that refuses to move, but the one that knows exactly how to bend. And honestly, that's what makes this kind of engineering so fascinating to dig into. The biggest, most reliable solutions in the world often turn out to be the quietest ones, hiding in plain sight in a shape most people drive past every day without a second thought, dismissing it as just another smokestack or industrial eyesore. Next time you spot one of these towers from the highway, with that unmistakable pinch at the waist and a soft column of vapor drifting off the top, you'll know you're not looking at a chimney at all. You're looking at roughly a century of failed timber, cracked concrete, collapsed neighbors, and one very stubborn idea about how to make air move on its own. If this is the kind of hidden engineering story you find genuinely interesting. There are plenty more structures out there with secrets just as strange waiting to be uncovered.